Good morning and welcome you all for today's class. Yesterday we have discussed about Joule-Kelvin coefficient and Joule-Kelvin expansion for real gases to achieve cooling and heating. And so many applications of cooling and heating are there in various engineering processes. So today by using Maxwell relations and TDS relations, we again discuss about phase transformation. Clausius Clapeyron equation. Clausius Clapeyron equation, or simply we can say Clapeyron equation for phase transformation. Because one thing is clear that during phase transformation, once body or any material changes its phase from solid to liquid, or from liquid to gas, or from solid to directly vapor state. In all three cases of the phase transformation, temperature remains constant. So we will define how by using Clausius Clapeyron equation we can discuss what is happening during phase transformation of the material. So we will discuss phase transformation curve by using pressure and temperature graph. So let us start what happened in phase transformation. We see that during phase transformation that entropy, because during phase transformation either heat is released or heat is absorbed. So entropy will change. Entropy of system and surrounding will change, and during phase transformation volume will also change. So by using these two things and by using Gibbs energy function, Gibbs energy potential, we can define phase transformation, first order phase transformation. So let us see what is first order phase transformation defined by using Gibbs energy function. So during phase transformation, we see Gibbs energy function can be defined as dg equal to VdP minus SdT. This is a SdT. This is a Gibbs energy function with the help of also known as Maxwell relation. So here we can define during phase transformation. We know that volume and entropy will change. Suppose during phase transformation volume is changed like this. V equal to at any time V equal to 1 minus x Vi and plus x Vf. I means initial condition and F means final condition. So initial the volume at any stand of the during phase transformation, volume of material, volume of substance, given quantity of substance at any stand V, specific volume meter cube per kg equal to x means percentage fraction of phase changes, means if there is a solid changing to liquid, so x is fraction of the solid that is changing into liquid, and remaining will be initial phase 1 minus x Vi, that is solid state, and what is percentage x fraction changing into liquid state. And same thing we can write for entropy, S equal to 1 minus x Si initial condition plus x into Sf final condition. So these are two transformations, and we can see here from the equation number 1 how we can define from equation number 1 how we can define V, volume. We can define volume V equal to del G by del P. Del G, derivative of del G over del P at constant T. And same thing we can define entropy change, S equal to del G by del T at constant P by using equation number 1. So here we can see in first order phase transformation volume changes and entropy changes and derivative. You see that in first order phase transformation volume and entropy changes you can define by this equation, and derivative of this function, Gibbs energy function, derivative of this Gibbs energy function or discontinuous. You can see because discontinuous, V is del G over del P at constant T, and then S del G over del T at constant P. So it is a discontinuous function. Changing at 2 points, you can define volume change and entropy change in same equation, Gibbs energy function dg, by taking two parameters. These two parameters are different. So in first order phase transformation, volume and entropy changes and derivative of the Gibbs energy function are discontinuous. In first order, that can be defined as what is characteristic of first order phase transformation means that volume and entropy changes, and derivative of this function is discontinuous. You can see first volume change del G over del P at constant T, then entropy change del G over del T at constant P in same equation. That's why we can say derivative of the given energy function are discontinuous. Now let us define another equation, TdS equation, by using Maxwell relations. TdS equation we have defined for volume change. TdS equal to dV dt and plus T del V over del P over del T at constant V dV. This is a TdS equation. First TdS equation based on the specific heated constant volume CV, and we know that in phase transformation what is remains constant. Here dt is a exact difference here. So during phase transformation dt remains 0 because t remains 0, so dt will become 0. So this term becomes 0. So equation you will get TdS equal to 0 plus T del P over del T at constant V dV. So now you can say what is TdS? You can replace temperature and temperature because and dP over dP over del T at constant V equal to ds, change of entropy upon dV. So we know that dq during phase transformation one thing also occurs, latent heat of phase transformation. During phase transformation either latent heat is absorbed or released. So we can define latent heat L equal to TSF minus SI, because we know that during phase transformation entropy changes and temperature remains constant. So we can define L can be defined as L equal to, also defined as HFG. If phase transformation from fluid to gas, then we can define L equal HFG equal to T and change of entropy SF minus SI. This can be also defined as enthalpy of phase transformation. So here we see that del P over del T at constant V. So del P upon del T is independent of volume. We can write this equation. Suppose let us reduce its size. So L equal to HFG. We can define L latent heat of phase transformation equal to T SF minus SI. And equation already we have get del P over del T at constant V equal to ds by dv. We can write SF minus SI upon Vf minus Vi. Change in volume, change in entropy, final entropy, initial entropy, final volume, initial volume, and multiplying this equation we can write also because it is independent of del P over del T at constant volume is independent of V. So we can write dP, simply we can replace this equation dP by dt equal to SF minus SI, final entropy minus initial entropy upon Vf minus Vi. So multiplying whole equation right side by T temperature, we can write this way, multiplying by T SF minus SI upon Vf T Vf minus Vi. This we can write as, but because T del, you know Q equal to T delta S or dq equal to TdS. By using this relationship, we can write this is enthalpy of phase transformation, or you can say latent heat of phase transformation. You can write it is like L, latent heat of phase transformation upon T Vf minus Vi. So this is the equation of the phase transformation. It is also known as a Clausius Clapeyron equation. dP over dt equal to L upon T Vf final volume minus initial volume Vi. So this is also known as a Clausius Clapeyron equation. Clausius Clapeyron equation of phase transformation. This Clausius Clapeyron equation of phase transformation, this is very useful in defining nature of the phase transformation graph of any material, and also what is the slope of the phase transformation curve. So now see here in next page we have derived equation dp over dt equal to L upon T Vf minus Vi. Suppose Vf is a liquid state. We can first draw a graph. Let us draw a graph. P and T, pressure temperature graph of phase transformation. This is solid state, solid, liquid and vapor. This is a critical point. This one is a triple point. TP, TC, critical temperature. Vaporization curve. This one is a vaporization curve. This is a fusion curve. Because here in this side, solid changes to liquid changes to solid. From this side to this side, liquid changes to vapor changes to liquid. So it is a vaporization curve, and any point this is a from here to here solid changes to vapor. So this is a sublimation curve, directly sublimation curve. So here this is this region vapor solid directly converted into vapor. We have so many examples. For example, that is a Kapoor, we know, directly converted into vapor form. So this point is known as a triple point. In this point, all three phases coexist at same temperature. That's why it is known as a triple point. So we can define slope by using, suppose here changing from this side solid to liquid. We define the Vi equal to V dash, that is a solid, and Vf by V double dash means a liquid. So here we can define the slope dp over dt equal to L of fusion, L upon T V double dash minus V single dash. Suppose here this phase transformation taking in this region, liquid to vapor, then a vapor form will be defined as triple dash vapor phase volume. So here dp over dt can be defined as dp over dt and be defined as L vaporization upon T. T means the temperature at which vaporization will take place. T upon V triple dash minus V double dash. For all three phases, phase transformation can be defined. Suppose here phase transformation taking from this to this solid to vapor. In this case, we can define dp over dt equal to L. Here L, latent heat of sublimation, SB sublimation upon V triple dash T into V triple dash minus V single bar. This, so what is dp upon dt? dp upon dt is nothing but slope. dp over dt is a slope of this curve. Any point. Suppose this is a point. Let us remove this one first. I want to define slope here. So see here slope. This one is a slope. This is theta, delta p over delta t. So delta p over delta t. If this difference is very small, you can write as dp over dt. This is a slope of the fusion curve or vaporization curve or sublimation curve. Any point we can find out the slope. So how slope will be defined? For example, this is for the only water. We know that during fusion, behavior of water is anomalous, and solid means water when solid form converted into liquid form, volume decreases, and liquid converted into solid, particularly for water, volume increases. That's why slope of this water fusion curve is negative. Here this slope is positive, this slope is positive, but this slope is negative because during for water when in fusion you can see for water, this is fusion curve, this one. Volume solid, when volume of solid is more than liquid, so it becomes negative. That's why because you know this is a solid state, this is a liquid state. For water, when water converted into solid, volume will increase. water converted into ice, volume will increase, and ice converted into liquid, volume will decrease. That's why this difference is negative. That's why fusion curve for water is negative. Slope of this one is negative, this one is positive, this one is positive, and this one is also positive. Due to nature of the water behavior during solidification or liquefaction, volume, it is anomalous behavior. That's why this curve for water, this fusion curve for water is negative. Now let us see, define this equation further. Let us take a vaporization. Vaporization curve. So dp over dt, dp over dt equal to L vaporization, you can say HFG T V third minus V second, because second suffix we have defined for this is liquid state and this is a evaporated, and LFG, L vaporization you can write HFG because fluid to gas changing, volume changing from fluid to gas, V third minus V second. And we know one thing clear that here volume of the liquid, this one V second is very less compared to V third, because you know that even for water, 1 cubic centimeter of water changes into 1617 cubic centimeter of the vapor. So this is a huge volume. This is very insignificant compared to volume of the vapor that is formed. We can neglect this one. So we can neglect it. Equation will reduce in this form. dp over dt equal to L vaporization upon T into V third. And we know that PV equal to RT. So V third equal to means the vapor volume, specific volume of vapor equal to RT by P. In this value of RT by P, so dp over dt equal to HFG upon T into RT square by P. RT by P. This is equal to HFG upon, here is also T, so RT square into P. Upper P will be coming to denominator. So dp over dt equal to HFG P upon RT square. Take here dp over P equal to HFG dt upon RT square. Integrating this from initial pressure to final pressure, dp over P equal to from P1 to P2 equal to HFG upon R, T1 to T2, dt over T means minus T square minus. So now we can get ln, here we get log P, P2 by P1 equal to HFG upon R minus 1 upon T, T1 to T2. That is equal to HFG upon R 1 upon T1 minus 1 upon T2. 1 upon T1 minus 1 upon T2. So we can get any, suppose initial pressure is P1 equal to atmospheric, that is 1.01325 bar, and so we can write at 101.325 kilopascal. So P2 by P1 equal to exponential HFG upon R 1 upon T1 minus 1 upon T2. So here we can write P2 means P, and if P1 equal to near atmospheric condition, then P2 equal to P. So P equal to 101.325 exponential HFG upon R 1 upon T1 minus 1 upon T2. So this equation we can use for finding out pressure at any given temperature. If initial temperature is given, HFG is given, then we can find out pressure, because HFG for latent heat of phase transformation is given. We can find out any pressure at given temperature. T1 is defined atmospheric temperature. We can write T1 is atmospheric given temperature, and T2 is the temperature at which we have to find out pressure P. R is given. R is a universal gas constant. R equal to 8.314 kilojoule per kg mole. It is given for the any gas, 8.314 kilojoule per kg mole. By using this equation, another equation was defined by Troughton's, because he defined that at boiling point. He defined HFG upon T equal to 88 kilojoule per kg mole Kelvin. By using Troughton's concept, Troughton's given that for any gas at boiling point, he defined that HFG upon TB equal to 88 kilojoule per kg mole Kelvin. Troughton's concept. He defined that for gas, approximately HFG upon TB equal to 88 kilojoule per kg. So here we can define HFG equal to 88 TB. TB क्या है? What is T? So TB is a boiling point temperature of material, any material, boiling point temperature of the material. So we can find out vapor pressure at any given temperature by using Troughton's concept. So dP over dt equal to 88 TB upon T into putting value of this volume, specific volume in vapor phase. So that is equal to RT by P. That is equal to 88 TB and P upon RT square. Now TP, writing this equation, balancing this equation, dP over P equal to 88 TB upon RT square and dt. So now integrating this equation, dP over P equal to 88 TB upon R integration of dt over T square and TB to T, and pressure will be P atmospheric 2P. So now integrating this equation, equal to minus 88 TB upon R 1 upon TB minus 1 upon T. This is plus. So, and here ln P upon P atmospheric equal to 88 TB upon R 1 upon TB minus 1 upon T, multiplying this equation by TB. So 88 upon R 1 minus TB upon T. Now P upon P atmospheric, taking here L equal to exponential 88 upon R 1 minus TB upon T. So this equation now reduced into this form. Right here, P upon P atmospheric equal to exponential 88 upon R 1 minus TB upon T. Simple integration we have calculated. Now P atmospheric, already we know P equal to, we know P atmospheric equal to 101.325 kilopascal. Putting value of P atmospheric here, 101.325 exponential 88 upon R 1 minus TB upon T. This is equation that we can use for the finding out pressure of the gas at any arbitrary temperature, because TB is known as the boiling point of the gas, and R is already known, 8.3 It already defined. We have R equal universal gas 134 kilojoule per kg mole Kelvin. So TB will be given, and T temperature at which we have to find out pressure. Atmospheric pressure is known, R is known, and TB is given, and T is temperature at which we have to find out pressure of the gas. So by using this equation, we can find out pressure at any given temperature. So I think this is clear that how we can use a Clausius Clapeyron equation for defining slope of the vaporization curve, and which one having more steep slope depending upon what is latent heat of vaporization. If latent heat of vaporization for sublimation is higher, then its slope will be higher than other curves. If latent heat of vaporization is higher than latent heat of the sublimation, latent heat of fusion, then slope will be higher. It depends upon the what is the latent heat of vaporization, or latent heat of fusion, or latent heat of the sublimation. So this equation is very useful in defining phase transformation properties. How properties changes during phase transformation. So this equation is very handy to define phase transformation phenomena, whether it is a fusion solid to liquid, that is a fusion, or liquid to vapor, that is a vaporization, or directly from solid to vapor, it is a sublimation. So all phenomena you can define by using same equation, that is a Clausius Clapeyron equation. So I think it's we can solve very easy questions will come, and in next I will solve some questions based on the Clausius Clapeyron equation. Thank you very much for watching, and wish you very nice day.